Hello everyone, my name is Professor Tarranum Shaikh from Sabusuddi College of Engineering. My subject here today is Microprocessor and Microcontrollers and the carbon emission. My first video was about the introduction to microprocessor and microcontrollers. You can see the details of the first video which is uploaded on YouTube link. Second video is about microprocessor standards. And this is my third video, which is having the video outcomes of after learning through video, students will compare and analyze various standards used by microprocessor manufacturers, justify carbon emission calculations and carbon footprints, inclined towards more sustainable computer design. This is the microprocessor standardization table. All the standards, various standards are given which are used for manufacturing, during manufacturing of the microprocessor. You could see in detail here. The next slide about it. Here one more standard which I have mentioned is the Energy Star outlines a conventional profile for annual energy consumption. This Energy Star is the simple choice for energy efficiency. This has been designed by, or this has been a standard which is given by EPA. In business to consumer life cycle, the total life cycle greenhouse gas emission of the APU system compared with the latest AMD system, which is also known as Nile. So this APU system is offering greater benefits or better benefits than the AMD systems in terms of GHG gas emission. And it is also to be known that the computers account nearly 5% of the world's carbon emission. So this is the comparison graph you could see here, where you could see the APU reference system is having 40 kilograms of carbon dioxide emission, whereas of Nile or Nile reference system or AMD system is having 67.4. So if you could see the difference between them, having a calculation of delta, would see there is a 40.3% of difference, which is, so hence you could say APU reference system is better than the Nile reference system. So there is a calculator link given down below if you want as a reference. So the duty cycles for the Energy Star conventional profile are shown in the given table. So there are various duty cycles, that is T off, T sleep, T idle, and the values about them, that is what percentage of T off and T sleep and T idle is given in the table. So what is the period of having those off or sleep or idle is shown here. This is the energy consumption calculations shown here. This is actually total energy consumption estimation, that is kilowatts are given here. You could see with all the calculation and all the details about it. And then finally here it is given as average energy consumption kilowatt hour of a product life, that is equal to nothing but total energy consumption into product life. Now after having this calculation, we get the energy consumption in terms of kilowatt. We now need in terms or this phase energy into the units of carbon dioxide emission. So to have this an emission factor of 7.18 into 10⁻⁻⁴ metric tons carbon dioxide per kilowatt hour is been applied. Now this is again the calculation of PFC, which is also known as perfluorocarbons. So this is the equation given here, and the terms have been defined, very well defined here again. So the percentage contribution of the different stages of microprocessor life cycle on the overall, like APU reference system and Nile reference system with the process step, that is water fabrication, assembly, TMP, then using of the phases having of in terms of kilogram carbon dioxide emissions. Hence the total gives into the total terms of 100%, but you could see the stepwise what are the percentage. So APU is giving the better performance here, you could see again here. Then again electronic manufacturing sector and the number of reporters. So the second table is been showing this. So now what is the sector that we have considered as electronics manufacturing, as we only deal with the microprocessor. We are dealing this video with the microprocessor, hence I have considered only electronics manufacturing. So number of reporters, like in 2011 we had 56 manufacturing sectors, and so until 17 there were 51. So the next table is again about the manufacturing sector and GHGRP. GHGRP here is Greenhouse Gas Reporting Program coverage in 2016. So here we have considered again the electronics manufacturing, those companies only which we have seen in from 2010 to 2017. So here the estimated percent of industry facilities which were covered by GHGRP, that is 24 to 56%. Then estimated percent of industry emissions covered by GHGRP, that is 75 to 90%. The table 4 is the manufacturing sector, electronics manufacturing sector emission reported to GHGRP. So here you could see in 2011 it was 7.0 carbon dioxide emission, and in 2017 you could see there is 6.1 million tons carbon dioxide emissions. This figure shows the location and emission range of each reporting facility in the electronics manufacturing sector. So this is a report of the year 2017. Here you could see there are the red pink dots given on the graph, which indicates the emission of carbon in terms of metric tons, that is CO2e. The darkest point is having the largest emission, and this lightest and the smallest is having the lesser emission of carbon. Then here is a graph which is showing the carbon emission again, linear and non-linear graph it is been showing here in terms of million metric tons carbon dioxide emission. Then the percentage of reporters by range of emission. So these are the reporters percentage, like how many percentage of facilities are been shown here. The green one is for electronic manufacturing sector and the gray one is for GHGRP. So these are all direct emitters which are emitting the 1000 metric tons of carbon dioxide. Now after seeing the carbon calculations, their emission rate, and then the problem is how to have a better environment, how to have a sustainable environment. So hence, to have a sustainable environment we need a sustainable computers. So for that there are three challenges with us, that is data centers, embedded system and cultural change. In data centers we will be seeing design for energy proportional computing. In embedded systems we will see design for silicon reuse, and in cultural change multidisciplinary green thinking. Now here in the first data center we will see the energy proportion hardware here, which it is actually building a system that scale energy better with performance. Microprocessors are already good at this, except the leakage problem. Networking is bad but could be a lot better. Disks are bad and need new technology. So this is one thing that needs for energy proportional hardware. The second one is variable speed disk size hierarchy, and solid state flash state change devices. So this is the summary, that is large scale computing is rapidly growing energy problem. Solutions require multidisciplinary innovation, and global scale IT depends upon solving these problems. The second one is embedded systems, which is actually designed for silicon reuse. So resource use in silicon fabrication, which are 1.6 kilowatt hours per centimeter square, 20 liters of water per centimeter square, 3.3 billion active cell phone subscriptions, and many more. So this is the first thing. The second one is throughput. 280 million phones sold per quarter. Average lifetime of a phone, that is 1.5 to 2 years. Old phones sitting in drawers, but throughput of over 1 billion phones per year. 32 billion kilowatt hours per year just for microprocessor. The third one is biodegradable material, which is a plastics biodegradable, fire retardants are bad. Organic LEDs, transistors. Then next is microprocessor reuse, obsolescence resulting from rapid improvements, microprocessor food change, technical challenges of reuse, form factor can't. What are those technical challenges? Those are form factor, battery life, and ISA compatibility. And the next slide shows the semiconductor material flow diagram, which is actually an outline of workflow in the recycling plant. Here you could see the diagram and understand the better. Design for reuse. Design for several applications and lifetimes, not just one lifetimes. More severe wear out, added overhead to support different applications. Design for easier reprogramming. Design for easier reclamation and retasking. Then reuse summary. Silicon fabrication and disposal are serious environmental concerns. Reuse is a challenging goal, but we have to face the impact of our devices. Then finally, here we see that is a cultural change. Some sustainable technologies and practices exist, but managers and designers unaccustomed to the trade-offs need to develop frameworks and educate the next generation of technical leaders. Life cycle analysis. Sustainable systems require a higher level analysis, that is energy and carbon metrics. Exergy, which the exergy is actually an energy which is already available that to use, that is thermodynamic reference states. The final one is make friends with your local industrial ecologist. Reacting to the policy standards and policy standards that like Energy Stars, SPEC power. Standards need knowledgeable participants. Companies need to know how to respond to legislation and standards, and those are WEEE, ROHS, Energy Star. Multidisciplinary training. The goal for that is promote design with energy trade-offs in mind, like UCSB multidisciplinary program in energy efficient computing. Then PhD in major area with minor in other area. Minor courses provide multidisciplinary understanding. Finally, here we have is sustainability is a broad, compelling problem. Good technical problems, but most are multidisciplinary. We need to train the next generation of multidisciplinary engineers. Thank you.